Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. In today's episode, we're joined by Debajyoti Ray, founder and CEO of RivetAI, a startup producing AI-powered tools for storytellers and filmmakers. Rivet's tools are inspired in part by the founder's collaboration with the team that created Sunspring, a short AI-written film starring Silicon Valley's Thomas Middleditch, which you may have seen when it was making the rounds a while back. Deb and I discussed some of what he's learned in the journey to apply AI to content creation, including how Rivet approaches the use of machine learning to automate creative processes, the company's use of hierarchical LSTM models and autoencoders, and the tech stack that they've put in place to support the business. Before we dive in, a couple of meetup-related updates. First off, great news for those of you who missed the first round of our Fast AI Deep Learning for Coders study group. Sebastian Wien, who participated in the first study group, has stepped up to lead a second group through the Part 1 course. Next, if you missed the announcements on email and Twitter, we recently launched a new online meetup group that's much more conveniently timed for folks in Europe, the Middle East, and Africa. This group is being led by Kai Lichtenberg, who delivered a great presentation on capsule networks earlier this week for that meetup's inaugural session. To learn more or join either of these groups, please sign up for the TWiML online meetup at twimlai.com/meetup. All right, on to the show. All right, everyone, I am on the line with Debajyoti Ray. Deb is founder and CEO of RivetAI. Deb, welcome to This Week in Machine Learning and AI.
Thank you very much for having me, Sam.
So, Deb, you studied math as an undergrad at the University of Toronto and actually got a chance to work in Geoff Hinton's lab. Tell us a little bit about that and how your career evolved from that point.
Yeah, so I was a math major, math specialist at the University of Toronto, and I was at the same time I was really interested in programming and coding, so I wanted to combine kind of both of my passions. And University of Toronto, Geoff Hinton was one of the luminaries in the field. So really what drew me to the university and to math in particular is I wanted to explore the field of AI. And in my first year, I actually convinced Geoff Hinton to allow me to sit in one of his classes. And then at the end of the summer, I offered my programming services, as an undergrad researcher, and I was really fortunate when they allowed me to do some of the projects. But I got a taste of machine learning since my undergrad days itself, working with Geoff Hinton and other researchers in his lab, especially in the field of Bayesian neural networks. And I had several publications coming out of it during my undergrad. After that, I wanted to explore the field of computational neuroscience and dive into neuroscience a little bit more. So I moved to London. But at that time, there was kind of a boom in the financial sector. So I made a digression into more hedge funds and quantitative finance. But in 2008, I also discovered that I wanted to go back to academia, explore my interests in deep learning and machine learning again, armed with a new set of applications. So I went back to grad school, went to Caltech in the Computation and Neural Systems group, and there my focus was more around generative models, because one of the advantages of deep learning models is it can capture very nuanced statistical behaviors, very complex statistical behaviors. So I wanted to see if that could be used as a generative model for to study different types of behaviors, especially like behavioral economics. So that's something that I pursued during my PhD at Caltech, but more generally looking at generative models for deep learning.
So from there, while you did start a couple of companies between your grad school experience and starting Rivet, there is that connection in that you were working on generative models there, and now you're currently working on applying AI to the idea of content creation. Maybe tell us a little bit about the inspiration for starting Rivet. What drove you to look at that problem?
Yeah, so from the business point of view, previously, my previous startup was Video Amp, which was in the video advertising space. It was looking at different behaviors, consumer behavior, and finding the best kind of video ads to target to people. But what I saw there was, advertising kind of sits on top of content. If you don't have good content, um, then you don't get the kinds of engagements. So that's one of the reasons why, companies don't get as much ROI out of their video advertising spend. And the other thing that I saw is like the shift that more and more companies wanted to put their money, instead of putting it into video advertising, they wanted to put it into sponsored content. Because at the end of the day, consumers, humans in general, we resonate much more to stories. So an ad is basically grabbing attention. It's 30 seconds to grab somebody's attention and, you know, maybe create, Pavlovian responses so the consumer will go and buy something. But what really resonates with us, forms culture, forms behavior, is story creation, story making. So there were a couple of, in terms of my own interests, um, I've been very interested in natural language generation. So when we look at generative models, especially generative models for language, I wanted to see how that could be applied to generate language. You start with a training set, but you also feed a bunch of different parameters. So can you actually produce narrative structures? Maybe even stories someday, right? Could a model generate a story? So that was my general kind of research interest, and also at the same time noticing this kind of shift in spend by companies from videos to content. The technology, especially the deep learning technology, was pretty ripe to be able to analyze content, because the tech has matured to the point where you can analyze videos, you can analyze audios. These things were not really very possible a few years back. So it's really the perfect like confluence of tech maturity and the business moving in that direction, and also it's my personal passion, which is what led me to start Rivet AI.
Maybe as a touchstone for folks, we can reference a project that folks may have come across. This is Sunspring. It was a short film that starred Thomas Middleditch, who's the star of Silicon Valley. And it was written by an AI, basically an LSTM. Tell us about that project and some of the ways you've worked with the team behind that since.
Yeah, so the company EndQ produced Sunspring, and when I was making my transition from video advertising to content, I teamed up with EndQ because EndQ is a production company that makes feature films, short films, animation films, and so on. And really, who creates the best content? It's Hollywood. So I wanted to partner up with the folks who really know how to tell good stories, who know how to create great content. And NQ was really the perfect partner, because one of the principals, NQ, is a Caltech trustee, Walter Korchak, and he has also like funded projects in AI and at Caltech. So that's how kind of we had a meeting of minds and wanted to explore the ideas even further. Sunspring was, a project where the tech behind it was essentially a very simple LSTM. So it's kind of like the same predictive text that you have from your phone. So imagine you created a story by taking every predictive response from your phone. So Sunspring was the seed word, and then you start with Sunspring, and imagine putting that into your phone, but something more complex. Obviously, imagine your phone's predictive response is now trained on movie scripts and has a little bit more of a complex LSTM, long short-term memory model, and you started using very simple maximum likelihood estimation and picked every word that came next, every next word that your phone suggested. So that's how that script was made. It was very simple. LSTM trained on um, sci-fi movie scripts, and then just maximum likelihood estimation. So from there, the real kind of genius in that project was the director, Oscar Sharp, who was able to take a script like that and turn it into a very interesting, watchable movie.
Interesting and watchable, but not necessarily intelligible.
Exactly. So, and really kudos to the actors and the director for making something out of it. So, but it was a very interesting experiment. That very few people would be willing to do, and so that experiment was like, what if we could actually take some model like that and turn it into a movie? What would that look like? And the response has been very kind of bimodal, in the sense that some people love it and love the idea of what it represents. On the other hand, there's hate. So whenever you get a bimodal response but lots of responses, that's when you know you're onto something and that you have to pursue that. So we made several iterations, especially with Rivet AI. We made several iterations on top of the models before, and we came up with the next generation of AI written content after that. But also our philosophy changed quite a lot, which was Sunspring, was one where it was completely unsupervised. It's a completely unsupervised maximum likelihood estimation. Let's create a script, and there's absolutely no direction involved. Whereas really, if you're telling a story and the story has to make sense to an audience, then two ingredients are super important. One is knowing the preference functions, right, of who your list or who your audience is. It could be in the form of general audience data, or it could be in the form of something that interacts with the director and tries to learn their preferences. And the second part is some sort of physical or even a cultural embodiment that AI program completely lacks. So imagine just an alien showing up, or worse, and trying to just generate something with no idea of what the context is at all. So what we focused on in our next set of models was to really put a sense of context in that, and also learn preference functions, whether it's a human interaction through a human interaction with the director or writer, or audience responses. And so that kind of evolved into our next set of models. And our philosophy now is not so much AI written everything, or AI autonomously generating content, or AI autonomously writing stories, but AI augmenting creativity in a couple of different ways. One is AI augmenting creativity because a lot of the creative process, for those who are actually engaged in making content, a lot of the process is very tedious. 95% of the time goes into the tedious stuff, and only 5% on inspiring creative works. So our tech is more focused on augmenting the creative aspects and trying to, where possible, take away or automating a lot of the tedious aspects.
Can you give us some examples of where the tedium comes into play in this particular use case with this kind of content creation?
Right. So, for listeners who are not in the content creation process or filmmaking, the typical flow is, you have a story, a script. Everything kind of starts there. And of course, there's a whole lot that goes into making a script. But let's assume we start with a script. Now, the first decision is development, like whether you actually decide to work on the script or not. So usually a studio or a production company will get lots and lots of scripts, and they have to evaluate whether they want to produce it or not. So usually in the industry, it's kind of surprising how even when you have these amazingly huge budgets, there's not a whole lot of data that goes into that decision making. So there are different ways you can incorporate data into that decision, whether you want to go with the script or not, whether you want to analyze that script, make some predictions of how well it would perform, and so on. So let's say you decide to go with the script. Now, the first point is, first step involves a script breakdown. So a script is essentially just words on a piece of paper, but they need to be depicted physically, or through an animation. So it has to go from words to actual physical representation. So that is a very tedious process. You have a 200-page script. What happens now is someone goes in with a marker and starts going through the script word by word, saying, okay, this here is a character. The character says this, so we do need a person here in a speaking role. Or it could be, and they're sitting at a coffee shop talking about this, so you need to have a set with a coffee shop, and the lead actor, he takes a sip from a cup, so you need to represent that cup as a prop. So there's so many elements that goes from telling the story to actually putting it in production. So that is something, that piece itself is hugely time consuming, several weeks often, but that's something that we can solve with natural language understanding, because we can, with a training corpus of previously annotated scripts, we can identify where characters need to be represented, where props are required, what kind of sets are involved, set dressing. Do you need a vehicle? Do you need a animal in that script, animal handler? So all of those, like that script breakdown process, can be automated, but there needs to be a better set of training data for that, because films always involve analogies. So you can have a sentence like buzzing like bees. So you don't actually have to have a bee in the scene, just an analogy. So those are
right.
those are things that kind of the AI needs to understand.
It sounds like a very specialized named entity resolution type of problem.
Yes, named entity resolution that understands analogies, or where analogies are coming. So you have to have a context understanding there. So that's a huge piece that can be automated, like going from like few weeks to just a few clicks of a button. In a few minutes, you have a script breakdown. And then from there, the next phase is, once you've got, okay, I need for over 200 scenes, every scene I need these parts and this actor and this location, then it's kind of a scheduling problem, a budgeting problem. So even the first phase, which is budget approximation, that again is a hugely time consuming piece. But since we have all these entities extracted, and we have training data from budgets and how these entities map to different budget estimates, we can construct budget estimates very quickly. Same thing with schedules. You have so many parameters. You have a certain location where a film needs to be shot, and this actor who's extremely whose time is extremely expensive. So how do you combine these to get the best schedules in terms of both cost and time effectiveness? There are billions of parameters to deal with. That is often done manually in that industry, surprisingly. So just automating a lot of that, just bringing in AI scheduling tools, just gives you 10-15% efficiencies right off the bat, which for these $100 million budget productions, are substantial savings. So those are the tedious parts of just content creation, where AI can come in and automate and provide budget and time savings.
Do you remain involved in the creative content generation side as well, or have you mostly, I think of the various things that you've described as content support, but more on the analysis side, if you will. Do you tend to focus on that as a company now?
Yeah, so we have also been bringing in different kind of tools, but slowly. So first, it's kind of whenever we try to talk about AI in the creative industry or content creation industry, there's a bit of resistance initially. So it's also a different strategy for kind of entering the market. So starting with analysis, starting with things that save time and effort, builds more comfort in allowing people to understand that yes, AI tools can actually help my work. The analogy that I draw is AutoCAD, right? You had architects who, where it was always considered to be a very creative endeavor. Nobody touched my clay models. But then AutoCAD came in and took away a lot of the tedious aspects of architecture. And now it's hard to imagine, creating these complex architectural models without using computers and AI tools. So the same thing, can happen in the field of content creation, but incrementally. So one of the features we've added in is things that make the writing better, but in the sense of, hey, can we make it more readable? Can we make it, improve readability? Can we improve audience appeals? So, for example,
I'm thinking like Grammarly for scriptwriters.
Yeah, I mean, Grammarly, improves. It's targeted to a very broad audience. So imagine for something where people are creating content where you can take something that was, let's say, readability level 11, and if you turn that into readability level 5 or 6, then you can show that it'll appeal to a much broader audience while keeping the fundamental idea, the story, everything the same. You're just kind of changing some of the words, right? And simplifying the sentence structures. But all of a sudden, you've reached a much wider audience. So that's an example of how you can augment the writing, augment the creation. The other pieces are, with the short films that we have created, where the dialogues are actually generated. Some of the AI characters, dialogues are generated with natural language generation. So what is different with that from previous LSTM models is, I described the script breakdown. Now, the next thing you can do is you can also look at character interactions. So in scene 1, let's say you have Peter and Amanda interacting, and scene 5, they interact again. You can look at the words that they've spoken. You can look at the sentiment of their interactions. You can even look for continuity by analyzing the sentences that they've spoken. So imagine doing that for a movie or even a TV series. So you can turn a script into a knowledge graph, basically, which is characters and their interactions over a period of time, and use that to identify any continuity issues or things that trail off. Like it could be just a story sideline that trails off and doesn't really add much to the central theme. Now, for writers, imagine like Westworld, there's so many little subplots going on, and when you go into a writer's room like that, it was kind of eye opening for me going into a writer's room where the wall is literally covered with sticky notes and strings tying things together, and the scripts are ginormous. So that's something that's really hard to do, where again, bringing in tools like visualization tools, and even a step further like continuity analysis, looking into things that trail off, or that improves the content generation a lot. But you can take it a step further, which is, let's say now I want to make certain changes to the story itself. So I have a knowledge graph, and I go to a certain node, which is characters interacting, and I want to move around and play with. Let's move the story around and let's see what happens. So there you can actually use Bayesian inference to figure out what would happen to the rest of the nodes if you make a particular change in one node. So those are the different ways that we can give tools in the hands of writers and producers so they feel free to change around different parameters of the story. Now, something we can't do right now, but we're working towards, is also mapping that to audience response data. So perhaps you can make tweaks to a story, in a way that will be more interesting to the audience. Or maybe you want to try something completely new just to experiment and see how the audience would react to something.
Can you talk through the knowledge graph and the use of Bayesian inference at the next level of detail? How do you translate that? For example, translate that knowledge graph and Bayesian inference to something that's to an output that a scriptwriter can use.
Right. So as an analogy, you can use knowledge graphs have been used in a lot of different domains. So let's say in the case of genetics, right? So you look at pairwise interaction in one place, and then you can use Bayesian inference to say, okay, what if I made a change here, like the genetic code here, how does that influence things in other parts, right, in connected nodes? In more of a causal model, where the underlying causality, you can make tweaks to one node, and you have a causal model that will tell you what happens as you move one thing and change it, and the effects that it has further downstream or on the rest of the graph. So we have certain models of sentiment and models of emotional interactions and character interactions. These are not like models that you can necessarily write down, but more correlational that we've picked up by breaking down lots and lots of scripts out there. So there's a universe of 50,000 scripts that may have been produced, an order of magnitude more if you look at scripts that have never been produced. So you can do this exercise with, produce knowledge graphs for every script out there and learn some of these interactions. Now, the way we learned our interactions is we had people go and code these interactions or annotate from one node to another what the sentiment interactions were. So we were able to use that data to train kind of like a sentiment causality graph. If you change the words or the sentiment of one node, how does that impact the others downstream? So that's kind of like a high level version of how we can use a knowledge graph to see, predict what would happen down the road.
How are we representing sentiment? Is it like trying to apply human emotions to these things, love, hate, whatever? Now, I'm really just trying to wrap my head around maybe a concrete example of how a script might apply or translate into this model, and then how manipulating this model helps us with the script process.
Yeah. So, the simplest example is, let's say Paul and Andy are in a fight and Paul kills Andy.
Mm-hmm.
So now all of a sudden that character Andy can no longer exist in the rest of the scenes, right? So that's a very simple inference that you can apply to the rest of the nodes. Let's get more complicated. Paul and Andy fight, but then they realize they're working towards the same common goal. So therefore, their interactions now are positive. So now the rest of the nodes, if the next node where Paul and Andy interact was a negative interaction. So for you to change Paul and Andy's interaction to a positive one, that creates a big difference. Like you basically leave an explanation gap between your node now with Paul and Andy's interaction and the next one. So those are basically gaps that you can look at in the interactions, the characters' interactions that become fairly easy to identify. Now you can get a lot more nuanced, but what we see in scripts generally is that's not really necessary. If you look at successful scripts and look at their knowledge graphs, they tend to cluster into very fairly predictable storylines. So there's if you just map the sentiments, there are certain things like the hero's journey or the fall from grace. These are things that even Aristotle wrote about in the Poetics. Identified a certain set of story archetypes, and things haven't really changed even after we analyzed all these scripts. These common themes reappear. It could be because humans tend to respond to those type of storylines. So at a high level, that's kind of a mapping to understand what is the general storyline from the knowledge graph. The second phase after that is, again, in terms of good storytelling, there's always a tension and resolution happens throughout. So if you look at good storytelling, it's never a flat affect all the way through, because that doesn't make for an interesting story. But something always happens, right? Even if you're writing a story about somebody doing research, it's not like they kept working night and day and then found a solution. It's like, no, they worked really hard. They were close to a breakthrough. Then something happened and their world came crashing down. The next day, like one of the relatives entered into a car crash and they got depressed. So there's always has to be something. You need that volatility in a story just to attract the audience. So those are things that can be extracted, without necessarily going too deep into kind of an emotional analysis or sentiment analysis of the script. Even like more higher level things that we can extract, like positive, negative interactions, friendly, unfriendly interactions. Those are things that we can extract from the script, and that can give us a very good read into how well it would resonate with the audience.
You've helped us understand the problem that you're taking on, providing essentially creative support for script writers, in many cases centered around this knowledge graph. And you've mentioned, using techniques like Bayesian inference. But in trying to apply kind of the full breadth of machine learning, NLP, NLG, NLU, all of this stuff to these types of problems, I'm curious if you can talk through just what are some of the roadblocks that you've run into applying, things that may have been created in some research lab to, practical tools that you're trying to put in the hands of script writers, and how have you overcome those challenges?
Yeah, I mean, we have had to develop a lot of new methods along the way. So, one of the big challenges whenever we deal with generative models is a lot of the research papers. They look really promising because you read it and it looks like this natural language generation technique really works. But a lot of the times it could just be really handpicked answers, handpicked solutions, and working with that very specific kind of data set. So, LSTM, right? That was an experiment we did. If we could just generate a script using LSTM, what it would look like, and we ended up with Sunspring. But in trying to make that useful, we realized a lot of gaps, right, in where academic research is right now versus what we need to create this full solution. So with LSTMs, we needed to augment those models in a lot of different ways. So first, context becomes super important. Also, we modified those models to involve active learning because we wanted to learn preference functions. We wanted the model to we wanted to train it more iteratively. Also, we started looking at conditioning on like the knowledge graph to generate dialogue or generate next responses instead of just an unsupervised solution, which a lot of these LSTM-like models papers they talk about. So just from model architecture and coming up with new solutions, we had to take many steps beyond what was currently shown. And so a couple of things. One is, it may not be a great academic paper if you just combine context plus memory models plus hierarchical models into one solution and show how great the results are. A lot of the machine learning papers or publications center around coming up with a whole new model and showing the mathematics behind it, and that's what ends up getting accepted to NIPS and ICML. So a lot of that research is not necessarily directly applicable to what we're doing, whereas it's kind of like more around engineering the solution. So there's a lot of engineering work that goes in, which may not be the most interesting machine learning advance, like a new model advance, but it's still pushing the results and the applications a lot along the way. So that's more on the model side. And I think something that there's been a lot of work in on the generative side. There's been a lot of work in images. So we look at sharp-looking images that have been produced by GANs, and that's why GANs have become such popular models. But that GANs don't work very effectively when you're looking at natural language generation. There we have found autoencoder models to be much more effective, partly because the GAN objective function, it starts pushing it towards defining the posterior distribution very sharply. So that's how you end up getting very sharp, realistic looking images. But when it comes to natural language generation, it kind of produces the same very predictable sentences over and over. So that's where something like an autoencoder model works very well. So these are certain kind of findings that would be interesting for researchers to explore, but that doesn't really fit into a lot of the current academic models or current models of what's a more interesting publication over another.
So you mentioned a few things in there. One is hierarchical LSTMs. What are those, and how do they come into play?
So Sunspring, it all came about because we wanted to improve the model beyond Sunspring. So an LSTM, long short-term memory model, it does a better job than an RNN in terms of long-term dependencies. So an RNN tends to kind of forget, what was the word that was like 5-6 sequences ago, whereas an LSTM tends to remember. So like within a sentence, you get more coherence. But there's still limitations. So if you keep producing coherent sentences, that doesn't make for a story. So let's add more structure to that. So now if you're with a hierarchical LSTM, you can learn dependencies across sentences, for example. So now your paragraph that you produced becomes more coherent, more understandable. Now you can take it a step further. Now you can define hierarchies, right? It could be paragraphs to sentences to words. It could be even beyond that. It could be multiple paragraphs to sentences to words. So these hierarchical LSTMs provide more consistency in the sentences or the words that have been generated.
Are you training them hierarchically as well, meaning independently, or are they? Is it a model that you're training end to end?
Yeah, that's a very good question. So when we tried to train them purely unsupervised, the hierarchical models, you do get consistency across paragraphs, but that's not necessarily the most useful when you're trying to generate like stories or do something interactive with a story writer or director. So we had to use a lot of like annotations. So these annotations were basically, we had human annotators saying these paragraphs depict the same idea, or we had encodings saying which, if you're using purely hierarchical models, then every paragraph would be sequentially, we'll make the assumption that every paragraph is sequentially, follows a sequential format. That's not necessarily the case with stories. So we had to tag these stories by paragraph or by even sentences to say this relates to that paragraph from page 3, section 2. So those are the longer range dependencies that we could train our model on because we had the annotated data.
It does strike me that a lot of the challenge in what you're doing has to do with, how do you represent these different contexts or these different concepts and contexts for that matter, and the relationships between them, and, what are the properties of, I guess you can get arbitrarily detailed with this. Like, what are the properties of a given prop? And, is there some inconsistency in the way this LSTM is trying to generate someone's use of a prop? Or you're probably not trying to go that far, but have you learned any secrets or tips for, just dealing with this representation problem generally?
Yeah, so in terms of representation, that's why we found that the knowledge graph is the most efficient structure for learning or encoding these dependencies. It's the most succinct representation of these dependencies. So now we augmented our model so that even for the LSTM, it's conditioning on all the output is conditioned on the state within a knowledge graph. So let's say you have dialogues, right, that you're trying to generate for a character. Now node number 5 is where, let's say node in scene 5 is where we need to generate new dialogue. So we could either go with everything, all the words that were written before, or we represent the state of node 5, and then the LSTM generates output conditioned of how you've encoded that state in node number 5. So that's a much better representation, and I think more research needs to be done in looking at these knowledge graphs and how you can condition on these knowledge graphs to do generation.
I'm curious if the concept of embeddings comes into play when you're building these models.
Definitely. So you can't just rely on just straight up words, because again, when we're looking at words, embeddings becomes very important. You have analogies, you have similarities. So we have to learn. We base everything on learning a word and embedding first. And generally, I mean, that's it's the whole natural language generation and understanding is a very interesting problem in its own right, because everything is so context dependent compared to, let's say, image recognition. And that's why you have a company like Google and Facebook, because they have the largest data set of images. You can see the most variation in that data, but that doesn't necessarily work so much when you're dealing with natural language, where you really have to focus on focusing on a particular vertical gives you much better results than trying to go after a broad problem. Some of the natural language processing APIs out there cannot even get anywhere close to what we want to do, because they're going after a lot of breadth in their responses. So that's why, in terms of like understanding sentences in their context to a given depth is very difficult, because context changes kind of so much based on the domain and the vertical.
You also mentioned autoencoders. Can you share a little bit more about how you've used those?
Yeah, so autoencoders we've found work very well with natural language generation. So what an autoencoder does is, the input layers have some number of nodes. The hidden layers actually have fewer nodes than, or fewer units than the input layer and the output layer. So what an autoencoder does is it starts with a large number of input nodes. So let's say 100, and the output nodes could be another 100, but the hidden layers would be fewer, like 20 nodes. So what that forces the autoencoder to do, because it's using fewer nodes, fewer units in the middle. It has to compress the input and try to generate, the output of the same dimensionality, but it has to compress the data that's coming in. So what that does in terms of language is, it forces, one way of understanding it takes words and forces that into concepts. So let's say there's, the input is, you want to represent the idea that I take walks daily. There are different ways of saying that. Like, I'm a regular pedestrian. I occasionally walk around a lot. So the same idea can be expressed in multiple formats. So an autoencoder, because it's compressing the data that's coming in, kind of maps things, or is forced to map words into concepts in an unsupervised way.
Are you doing anything where you're taking those concept vectors from the middle part of the autoencoder and then using those as representations in your knowledge graph? Is that kind of what you're getting at?
Yes. So those kind of form, they're basically, they can form the states of the knowledge graph. So the state of a knowledge graph doesn't necessarily need to be something that is human interpretable. It could be, the middle layers of an autoencoder that could inform the state.
Oh, interesting. It's an interesting case study, perhaps, on the practical applications of AI, like all of the different pieces that you've had to put together to build this solution. Very, very interesting.
We started off in something that can be considered fairly niche, because these are scripts written for Hollywood. But from a business point of view, Hollywood itself is a very big industry. But even if you look at beyond Hollywood, it's the whole content creation industry is massive, in the hundreds of billions of dollars. So although it's a very niche problem, the economic impact of it is very substantial. It's going after one of the biggest markets. So at this point, still there's a lot of you know um, uh, trying different experiments, or taking different ideas, or taking different models and putting these things together. I think there's fundamentally more work that can be done, to build a whole new class of models that are able to take context, in different settings, able to encode relationships between entities, between people, and use that in generation. Now, that is a very interesting research problem to go after.
And so, as a startup trying to bring an AI product to market, do you see part of your contribution as kind of advancing that research effort, or is that outside of the scope of what you're trying to do? And if someone does it, great, you'll use it, but you're not in a position to push these research types of questions. How do you manage or balance that?
As a startup, we discovered a whole new market and set of applications. We started in Hollywood and analyzing scripts, because that data is plentiful. Like, there's a lot of public data available. But we found that a lot of companies, Fortune 500, Fortune 1000 companies, have the same need. They want to produce content. They all are striving to produce better and better content. So, we trained our AI, or trained our models on the best data out there, or we cut our teeth on the harder problem, which is producing really high quality storytelling, high quality content. That's what Hollywood is all about, and then applying that to a broader set of content creation that is very specific. Like, a particular company, they have a certain context in which they want to produce their content. So that our models basically translate over. So generally, I think, as a startup, we can't go after the broad class of problems and spend years dedicated to one or two uh, core areas. So our goal is to produce products that our end users want at the end of the day. Our end users are producers, production companies, corporations producing content. So that's who we are catering to. But along the way, we've discovered a lot of very good problems. And that's one of the reasons we have collaborated with a lot of universities. So we have strong collaborations going on with Caltech, and we've like hired interns to work on research problems very specifically, because I think like discovering these solutions kind of help the community overall, and I wish more and more people would look at these problems, because that's benefiting everybody. But also we can kind of discover, or we're always looking at the research findings. So we'll notice them before everybody else, and we'll implement them towards problems where we have a path to market. So that's our approach, which is trying to build the best product, but also keeping a close eye on research out there, and also funding and collaborating with research labs and universities.
It's been really interesting kind of chatting about how your path bringing this to market. I think there have been a bunch of interesting tidbits for me, but probably the most salient one is this, just all of the different pieces that you've pulled together to build a solution. And when I think about, what it means to build kind of a knowledge graph for these scripts, it strikes me as a really, potentially, challenging problem. Like in a lot of ways, it's not, although the scale is very different in terms of the number of documents that you're trying to incorporate into this graph, the challenge in a lot of ways doesn't seem all that dissimilar from what a Google's knowledge graph, in terms of the diversity of concepts that you have to represent in it, and the way you're pulling together all these technologies to support that is very interesting.
Yeah, thank you. And yes, the volume is less, but we do have a lot of complexity in the relationships and the data that we're trying to analyze.
Mm-hmm.
So as a result of that, we've had to build some really solid proprietary data sets. We needed a lot of annotations. So fortunately, we offered a product that brought us a lot of those annotations, and we could train our system. So that goes hand in hand. Landing on our products are used by production companies and producers. So we have the best data for this type of problems, and then we are looking for different ways to use that in enriching the knowledge graph, in producing better generative output.
Just out of curiosity, what does your technology stack look like?
Most of our models are coded in TensorFlow. We use Python. There's different on the product side. We use more Node.js and web interfaces. And for our knowledge graph and coding a lot of that internally, I'm a champion of OCaml.
A Lisp guy?
Well, OCaml
is related to that, right?
Yeah, OCaml is a functional programming language, like Lisp, but OCaml does a few other nice things. Like it has formal verification. That actually helps. I don't think the research community has really figured out how to make best use of that. But if you incorporate formal verification, you can do knowledge graphs pretty well. There's just some properties that you can exploit from formal verification to construct knowledge graphs. And also, OCaml has object. You can encode objects and classes. That means you can have you encode richer data sets that you can't do with Haskell and Lisp for sure. So functional programming languages generally, I think, are the way to go for programming in AI, because functions are primitives, and at the end of the day, you're you're doing lots and lots of functional operations on pieces of data. So I think like the whole AI community could do well to switch to functional programming languages from Python and other imperative languages that people use now.
Awesome. Well, Dave, thanks so much for taking the time to chat today. It's been really interesting.
Thank you very much for having me, Sam.
All right, everyone, that's our show for today. For more information on Dave or any of the topics covered in this episode, head over to twimlai.com/talk/178. If you're a fan of the podcast, we'd like to encourage you to visit your Apple or Google podcast app and leave us a 5-star rating and review. Your reviews help inspire us to create more and better content, and they help new listeners find the show. As always, thanks so much for listening, and catch you next time.